Hi, everybody. I think there are quite a few people here. That's nice. And yeah, I see there's still a few people coming in, so let them just give them a few seconds to find a seat. Nah, let's not wait. Too much to talk about tonight. So, welcome, and I'm here to talk about a topic that's very close to my heart, about securing these sensitive APIs. How do we share information in a very challenging environment? I've been working for the health sector in Norway for quite a few years now, and we've come a long way, so I got a lot to tell you about. Before we start, I should do an introduction. I'm from a small company called OAuth. We're basically 4 people, consultants working for mainly the health sector in Norway, doing some other projects as well, and we're specializing in information security, identity, data sharing, those kinds of things. And that's our tiny company. We are 4 people, 3 of us in Trondheim in Norway. And if you guys want to talk about stuff, we're always interested in new, interesting projects, if there is anything going on. The service I'm going to talk about is called HelseID, and it's owned and managed by Norsk Helsenett, the Norwegian health network. They are the provider of common health services across the entire health sector in Norway. Do lots of cool stuff. They have a booth down here. You really should go talk to them. I said that. I promised to do that, you see. Yeah, enough introduction. So, I'm here to talk about the Norwegian health sector and sensitive APIs. What is a sensitive API? In my world, a sensitive API is basically some kind of service that you really, 3 reallys, don't want people to have access to. That you only want to share with the right people, the right organization. And if that information gets in the wrong hands, if that functionality gets in the wrong hands, it's a disaster. These things really shouldn't and can't go wrong. In my sector in health, it's much about health information, like critical information about a patient, medicine lists. We have like treatment history and journal documents. And then you have, that's the type of information we share. But in addition, we have functionality. For instance, you can make prescriptions. And there's lots of money in prescriptions. If you can start making prescriptions to anyone, then the millions and billions go away. And so in my world, that's a sensitive API. In your world, that could be something completely different. In finance, it could be an API that lets you deposit or withdraw money, for instance. So a sensitive API is exposed somewhere, and in the world of APIs, we do open APIs, OAuth, OpenID Connect, that stuff. So you really need to trust someone, and you need to establish that trust, and that's basically what I'm going to talk about. I need to do a quick primer about the Norwegian health sector. I was going to ask, how many of you are Norwegians and know the health sector? Most, but not all. Let's do a very quick primer. Norway, it's not a big country, as you know, 5.5 million people. But the health sector is extremely complex. We are divided into what is called health regions, 4 regions that are basically their own companies. Then you have all the hospitals in those regions who are also there, do whatever they want, they run themselves. Then you have all the doctor's offices and all kinds of private clinics. And then you have the municipalities. There are hundreds of them in Norway. And all those are separate organizations who have their own responsibilities. They have the same responsibilities. If you are a hospital or you are a single-man doctor's office, there are the same requirements for security and also the same requirements for sharing information. So we have lots of actors, thousands of them, that all need to interact. In addition, we have the vendor market. So you could expect Norway, as a small country, to have basically one vendor that does everything. And that's exactly how it isn't. We have lots of vendors that make the software that also needs to interact. And that means that there's very much complexity to handle. And all these organizations that own these sensitive data, they need to trust each other. So how do we do that? That's why we are here, basically. My team and the organization I work for, we are here to help this health sector share information in a secure manner. Sounds simple, right? So we have a simple solution to that. That's a service called HelseID. I guess quite a few of you know it before. I've been talking about it on NDC for years. This has been an ongoing project. It was started back in 2015. We went into production in 2017. We're 5 years old this year. Someone needs to bake a cake. And we are basically a national trust service for this health sector. The idea is that everybody trusts HelseID, and as long as they trust us, then it simplifies data sharing immensely, because the only other option is for each and every actor to trust everybody else. And those of you who are good in maths know that thousands of actors trusting thousands of actors, that's a big number. While those 1,000 actors, everybody trusting the single HelseID, it's still a big number, but it's much smaller. So our service, it's basically an OAuth2 and OpenID Connect provider. We do user logon, federated via the national services, bank ID, bypass, Confidus, those. We offer single sign-on, so that when the health personnel has logged on to one service, then they are logged on to all services. That's a great boon for the health personnel who otherwise would have to log on to so many services. But the single sign-on and all that, that's a nice feature, but the big thing is the API security that we do. Since we know each and every system, organization, vendor in the health sector, we can establish trust. And by doing that, we give the basis for data sharing. It's always up to whoever owns the data to make a decision. But we can give them the information that they can trust and that they can use to decide. And since we are in a limited sector, we are in health, we have defined a very tight security profile. That's what I'm going to dig into later. And that fits our goals well. Not only is it secure, since it's tight, it's much easier for all the vendors to accept, and it's actually fairly easy to understand. So what's the problem here if HelseID is a solution? That is that all the organizations in this sector, they must share health information. It's not like they can choose to share information. They have to. That's decreed by law in Norway. So it means that no matter if they want to or they don't want to, they have to do this. And so we are establishing the ecosystem to do that. So since all these organizations, they are required by law to share information, what do they do today? What are the alternatives to building this ecosystem of systems or organizations, all that. What are the alternatives? Because there must be alternatives. And actually, the truth today is that there's lots of sharing of information on paper. You have couriers, people going with taxi, delivering paper to doctors. They do fax. You remember those machines, right? Beep. Then you get paper copy somewhere. And then we have in other countries where they try different approaches. Some try other technologies instead of OAuth OpenID Connect. In Sweden, they do SAML, which is an alternative protocol, much more complex, much more error-prone. It's doesn't offer anything better, I think. We could have the option of storing all the information in one place. That will reduce complexity so much. But at the moment, that's not a viable option, probably not legal, and there is no such option today, at least. So at the point where we are now, we need to establish trust between the organizations, and that's why we are here. And then we need to secure the APIs, these highly sensitive APIs. And my proposition today is that that's easy. It's a solved problem. Everybody knows how to secure an API, especially in a context like HelseID, where we are in the health sector. We have very clear requirements for how to build an API. We tell them how to secure an API. We tell them how to ensure that this API does access control correctly. Since we do OAuth, we explain to them, you have to verify the access token and all that. We have requirements in the Norwegian health sector. You have to follow what we call normen. It's the base standard for information security. How do you share information? How do you build information systems in the health sector? So building a secure API is actually quite easy. But the problem isn't to building a secure API. It's all the consumers you have. And like in my example, we can have thousands of consumers, different systems by different vendors. And your API is never more secure than the weakest consumer you have. And that's where the problem is. So securing the API is easy, I think. Easy enough. It's still a complex technical problem, but it's something we do. That's something we are able to handle. But establishing this secure ecosystem where we have the trust, that's the real challenge. Now, trust. What's that? I'm guessing everybody here has heard of Maslow's hierarchy of needs. Of course you have. And I want to show you a model. You know, you have the basics at the bottom. You need food, you need clean air, you need heat, you need a place to live. When you have those basics, then you can start working esteem, love, belonging. And when you have all that, then you can start to fulfill yourself, fulfill your dreams. So that's the hierarchy of needs. Of course, at the bottom, you have Wi-Fi. We must have that. And in our sector, we have defined a similar model, what we call a trust model, which also is a layer upon of not needs, but requirements. How do we build trust? You can't read this, and that's not the point. The point is that we are doing the layers, but I'll try to explain. We have a foundation of the shared normen, as we call it in Norway, the shared common understanding that everybody adheres to. How do we do information security? How do we handle that in the Norwegian health sector? So that's the basis. Everybody agrees on that. Then we start building trust. We start with the HelseID service, the security and the quality of that service. We spent years doing that, honing the security, tightening it. And people trust it now. We're very happy about that. And then when we have the service itself, which is considered quite secure, maybe that's a crazy thing to say in public, but okay. It's a challenge to everybody. Please hack us. But on top of that, we have standardized protocols. We build on OAuth, we build on OpenID Connect. These protocols have been studied for years by people much smarter than any of us here today. They have found flaws, they have found weaknesses, and they have found ways to correct them, to tighten them. And we are all the time following what is called the current best practice. And we are disallowing the unsafe functionality, which means, and we are requiring the additions to the protocols that fixes those problems. So we have secure and very standardized protocols that everybody knows how they behave. Then on top of that, we have, you see the white area, that's the security and the quality of the system, meaning the system that the end user uses, and the APIs. The security of these systems, that's basically our security profile, our requirements, and also other processes that build on top. And then on top of that, we have, for sharing information, health information, we need to know who the end user is. We need to know who the health personnel is. We need to know who they are, if they are the right person, if they're allowed to access this information. So we have a couple of known identity providers in Norway. We're very lucky there. We have, for instance, BankID, who is available for everybody, and it's a highly secure service. So you can trust the identity. We have strong authentication, and based on all that, we can offer what is called a security token to the client system, to the API, and the API can consider that information and give access if they agree that this information is good enough for our API. So I'm going to go into the details of our security profile. This profile applies both for APIs and for the client software that end users use. I'm going to use a couple of technical terms. Some of you, if you're not completely into the protocols, I'll try to explain, and I hope to have time afterwards for questions. I can't see anything from here, as I said, so let's take the questions at the end. So we have tightened the protocols, chosen specific mechanisms that offer the functionality we need, and removed others, so that we can fairly easily guide all the vendors who make the software. And that's everything from small private companies to Norsk Helsenett, the Norwegian health network itself. We all have to adhere to that profile. But since it's narrowed down, it's much easier to follow than the big entire protocol itself. I'll not go into laws and legal stuff. I'm not a lawyer. I don't know too much about that, and it's boring. I'm not going into the details of the tokens, basically the information you need to do access control. That's an interesting topic itself. We do a lot of discussions of that in the sector, but it's outside the scope for my talk today. And I talk a bit about process because that's important, but that's not what I'm going to spend lots of time on. I'm going to dig into the technical details. The first I want to talk about is OAuth. We are based on OAuth2, but in reality, we are on the upcoming OAuth version 2.1. This is a natural evolvement of the protocol where lots of insecure functionality has been removed. And a couple of security measures have been added as mandatory. This is based on several studies that have been done that have shown weaknesses in the protocols. And it's much of the basis of the security that we have now. And for those of you who are considering building an authorization server, go for OAuth 2.1. Don't go for the OAuth 2 profile. There are so many security hosts, and there are no reasons for anyone to go there. So 2.1, it's not standardized yet. It's not complete, but it's on the way, and it makes complete sense. Maybe the most important thing they do in the 2.1 profile is to remove what is called an implicit grant. Have any of you, are there anyone who knows this stuff? Not many. The implicit grants allow a web application to transport these tokens, access tokens, via the web browser. And we don't trust the web browser. The web browser is insecure, mainly by design. So the implicit flow, and thereby what is called a hybrid flow that is partially implicit, they are dead. We don't allow them, don't use them. If you do, you have a security hole, then you're going to be hacked. So we don't allow these access tokens, identity tokens in the browser, and we try to limit the information in the browser as much as possible. On top of removing this flow, we have some requirements. We require what is called PIXI, which protects against man-in-the-middle type of attacks. I'll go back to the details on that later. We do much stricter validation of the information we get from via the browser. We have limitations on how you use an access token. You can't use it in a URI, for instance. There are very specific rules for how to use the protocols. And actually, it simplifies the world for all our consumers. So we build on OAuth 2.1. In addition, we have what is called FAPI, the FAPI2 security profile. FAPI was, back in the days, an initiative for financial APIs. The banking sector, mainly. They were required to open up their APIs, so you can use one bank and you can get insight into your bank account at another bank. They do this, they are required to do this sharing. So they needed to do that in a secure way. So they made a security profile for OAuth. And this profile has been refined in its version 2, and it's not only financial anymore, fortified, some people say. You need something for the F. But it is for protecting APIs in what I call high-value scenarios. So it's exactly what we are doing. So it's the perfect match for us. This limits down the protocol use even more. You need to have what is called a confidential client. For those of you who know that, you know the consequences. We get back to that. And they add other measures that protects us against token thieves, basically. So it limits an attacker so they can't pretend to be your system, for instance. So it tightens down the protocols a lot. And that's a good thing. We needed that. So, woohoo, right slide. Let's dig into the profile. This is going to be a lot of details. It's going to be technical, so questions, please save them for later. And I'm happy to discuss them. So, a security profile starts with the obvious thing. You need to do web security. For instance, we require that all traffic is encrypted using TLS. We don't allow the old versions of TLS, at least 1.2. We absolutely recommend 1.3. No plain text, whatever, no matter what. We require all vendors to follow the OAuth guidelines. They need to know the top 10. We accept them to do penetration testing and all that, check for vulnerabilities. And we do also quality assurance of the applications. And these requirements, they're obvious. Everybody knows them. I'm going to say everybody follows them. But by having them on, not on paper anymore, but on a page that says you have to do this, these requirements actually gives a lot of value. And these basic requirements, of course, apply for an API as well as the client software the end user uses. And it also applies for desktop software, desktop clients. Because we are in the health sector, we are quite old-fashioned. Lots of thick clients on Windows computers, Windows XP, you know. lots of old software out there, but they still have to follow our requirements. They still have to be secure. So I said standard web security, but there could be standard secure software development. But this is a basis. Everybody agrees on it. Everybody has to follow it. And we can enforce the rules. And that's a good thing. So that's the basis our security profile builds on. And then we get into the details. We only allow what is called a confidential client. A confidential client is a piece of software installed somewhere. If it's a web software, it can be installed on your desktop. It can be some kind of client server type of software. It doesn't matter. A confidential client must be able to protect a secret so that nobody can access it. The end users should not be able to access it in any way. And neither should anybody else accept the software. The reason is that when we do protocols, we have two important information elements about that identifies and authenticates the software, an installation of the software. One is what is called a client ID. That's basically a username for this software. And then we have the secret. It can be a password, but I'll get back to that. But those two together uniquely identifies an installation of your software. And in the protocols, you can run without a secret. For instance, a pure single-page application. There's no way in the web browser to protect the secret. So then there's no reason to have a secret. So there are ways to use the protocols where you don't have a secret. You know the URL, you know what is called this client ID, the username of the application, and that's it. That's all we have. Then we do a user logon, for instance, and we're good to go. With our security profile, we don't allow those kind of applications. We don't allow pure web applications, pure single-page applications. You must have a backend. That's a cost for the vendors, but the security requirements, there is a reason for this. It is we need to know not only the person who logged on, but we need to know the software, and then we need to know the organization who owns this software. And then we need a secret. So we don't allow web applications due to this requirement. And we have a challenge with mobile apps and desktop applications. We actually haven't solved the mobile apps yet. We're not quite sure what to do. Luckily, there haven't been too much push in our sector. We are old-fashioned. So, but we do have desktop software, lots and lots of desktop software, and some of them are client-server type of software. They will require the server side of the software to store the secret away from the end user. But we also have simpler clients where you have everything on the doctor's computer. In those cases, we have done a risk analysis and see that they are approved to handling sensitive personal information, sensitive health information. And as long as a system is considered good enough to protect that kind of information, we have to accept them. So they are not proper, they're not proper confidential clients, but we accept them as good enough. It's a trade-off, but as long as they are able to protect health information, we say that, okay, you're good enough to protect the secret as well. But we still look into the measures they do. For web applications, since you have to have a backend, for those of you who are looking into that, look at the backend for front-end pattern. There's lots of documentation of that, many blog posts, frameworks, and everything. We basically, you use a cookie to secure your front-end application and the communication to your backend. And then your backend will serve as a proxy to other APIs. It's quite simple once you have looked at it. It's a very common pattern. So we only allow these confidential clients, even though it adds some limitations. These confidential clients could be set up with what we call a shared secret. That's basically a password. It's called a shared secret because both ends, both the client software and our service, in our instance, HelseID, we need to know the same secret. We need to be able to share it. We don't allow that. We say, nope, this is from the FAPI profile. And it allows us not only improved security, but also allows us new functionality. It allows the client software to send information to our service that can be digitally signed by with their secret, and they can then, we can trust it. They can tell us which organization are there, what do you know about the health personnel's contacts, what are they doing now? We can receive that information, we can verify where it came from, and then we can trust it. So this adds value for us as well. When we say Keypairs, that is a public-private key pair. It means that the installation of the client software needs to have a private key, a private signing key of some sort. This can be a certificate, for those of you who know that. It can be just a JSON web key, or it can be something else. We don't really matter. We care about the cryptography here. We care about the strength of the digital signature. We have some requirements. This key pair can only be used for this one installation of the software and nothing else. You can't use it to do other encryption. You can't use it in another software, only for this one application. But apart from that, we don't require a PKI infrastructure. You know, in Norway, we have what is called an enterprise certificate. We don't require those. They have been very popular in the health sector in Norway earlier. We don't like them. But we require the cryptography. So we require Keypairs. And on top of that, we have some quite strict requirements for the signing algorithms. It's not very important here today to go into the details, why we allow them, what our requirements are. The important thing is that we have requirements. They are in our documentation. They are available for everyone to see. And security is a moving target, as you know. So when a short elliptic curve is considered insecure, we can move the requirements. We require a longer key. And we can enforce that rule. That's what it gives us. And also for the vendors, they know what the requirements are. They know what they have to do. We do, of course, for those who care about that, we reject the missing signing algorithm. That's a known security hole in the protocols. But we basically have a list. These are the signing algorithms that we allow. So we have quite strict, quite clear rules on how to do digital signatures and how these things should work. Lots of details? Yeah. Then we have the protocol itself. We do OAuth and OpenID Connect. And for these sensitive APIs, since we must know who the end user is, there is only one way to use our service, and that is using the authorization code together with what is called PKCE. PKCE. This, we don't allow any of the implicit flows where the web browser carries tokens. And the reason is that these flows, they are vulnerable for so many attacks. I want to show you a basic flow, basic diagram that explains how the protocols works and the weaknesses. Why do we require this PKCE mechanism or what it is? So let's see. I drew this, the figures here last night, so I hope they work. Here we have our health personnel using their journaling software, something. This software requires the user to do a logon because they need to know who they are before they can access this API that allows you to do prescriptions, for instance. The software opens a web browser, either because it is a web software or it opens the web browser on the computer. send them to the HelseID web page. Please do a logon. The user, the health personnel, will enter their credentials. Say they go to the bypass and tap their FIDO chip, for instance. There are lots of ways to do this. We support them all. We will receive the information, yeah, this is Dr. Hansen, and we verify that information. But we don't send that information back to the client software. Instead, we send what is called an authorization code. This is just a one-time code that doesn't contain any information at all. But the reason we do this is that this is carried through the web browser. And we don't trust it. So we don't want to send anything there. So we return the authorization code back to the client software. Then, second step, the client software does a backend call to our token endpoint. It's just a different API on our side. In this request, they pass this authorization code that they got from the first step, but they also include an information element, basically a little bit of JSON that has a digital signature. And this digital signature is done with a private key, and that digital signature is the proof that this software is the software that it claims to be. So we are quite sure that whoever asks for this information is the software itself. And this request does not go through the web browser, so there is no way for the user to change it. Your browser plugins and all that stuff that can change how your browser behaves. And it's much more difficult for a man in the middle here, since this goes through a secure channel, secure backend channel. In HelseID, we will verify this information. We will look up that the authorization code matches a user logon that has been done. If everything is good, we reply back to the client software. Here is your token, the access token that contains information about the user, the software, the organization possibly, and which APIs the software is allowed to access. And then finally, the step 3, the software will call an API. They will include this token as what we call a bearer token. It's basically an authorization header that contains the text bearer and then the token itself. Quite simple. The API will receive this information. They will verify the digital signature of that token, that it is verified by HelseID. And if everything is good, they will look at the information there and do access control based on that information. Easy. But you see that we have 2 steps. We have one that is done by the web browser and one that is done by the backend. And there we could have a problem. Scary, right? A red figure. We could have an attacker that either is able to pick up the authorization code in transit, or it could rewrite the callback from HelseID so that they inject a new authorization code that is for instance, a different user or some other rights. Oops, sorry, that is my blood sugar. Don't care about that now. It's always when I do talks, my blood sugar goes up in the roof. So yeah, that's how it is. But this attacker, they can change the traffic and they can steal the information, and then they potentially can either change how the application behaves, or they can get an access token themselves that was meant for another application. And in both cases are quite disastrous because, as you see, this attacker can then call the API as if they are the other application themselves, or the other application can behave as the attacker. Both these cases are disastrous in our world, and there have been examples of these attacks in the real world. And that's what we want to protect against. Well, let's go back to the figure, but add 2 more information elements. In the first step, when user does the logon, they go to the same logon page at HelseID, but we include one extra value, which is called a code challenge. The code challenge is basically a huge random value, big random number, for instance. But the client software knows this value, but it doesn't pass it. They do a hash, a cryptographic hash of that value, and pass the hash. So they say, hey, I want to do a logon. Please remember this hashed value for later. So HelseID will store that value together with other information and remember it. And then in step 2, when the backend side of the software requests a token, they include the original value. And then on our side, we can calculate the hash of that long random value. And if the hashes match, the first one they sent and the hash we calculate, then we know with we can be quite secure, not guaranteed, of course, but we can be quite secure that number 1 and number 2 here, the backend, the front end and the back end, they are the same software. This is the same user session. So they fit together. And then we have the good situation where the attacker tries to tell HelseID, hey, please use this. I want to use this authorization code. And we can say, no, you don't have the code verifier. Or we can say that the code verifier doesn't match this authorization code. And we can stop you. That's a good thing, right? So this is why this is called the PIXI mechanism, proof key for code exchange. But PIXI, it's much more funny to say. And it's an extremely efficient measure. It's required in OAuth 2.1, but it's not required in the earlier versions of the protocol. That's one of the reasons you really should go there. But we have other attackers. Let's move the attacker one step down. After the client software has received this access token, and remember, the access token tells who the user is, it tells who the software is, it tells what they're allowed to do. If we have an attacker that steals this token somehow, let's not go into details how you do that. It can be unlikely, but if it's possible, then they can use that token to call the API. And the API has no way of discerning if this is the true client or if it is an attacker. We are still vulnerable. Of course, protecting the tokens, that's details of the security of the system. We enforce quite a few rules on how this should be done. But still, there is a chance that you can do that. So how do we stop these token thieves? Did any of you go to Dominic Byers' talk yesterday on Depop? That's exactly the solution. Depop, or more general, what is called the sender constraining of tokens. It allows us to ensure that whoever uses this access token against an API is the same application that this token was sent to. So we can ensure that we don't have an attacker in here somewhere. There are two mechanisms actually to do this. Depop is fairly simple, where the client software needs to possess a secret, and that secret, not only must it be used when requesting a token from our service, from HelseID, but when you call the API, you need to prove that you still possess that secret. So as long as, and that's some kind of signing key, private key. And as long as you possess the secret, then again, there are no guarantees here, but we can be quite sure that whoever uses this token is your application. We have an alternative mechanism called mutual TLS, where instead of the application creating this secret, they are based on the TLS connection to the web server. And they use that key as a proof in the later requests. In our environment, in the health sector, we do lots of reverse proxies, TLS termination. So using that mechanism isn't... It's possible, but Depop is much easier. So we prefer that mechanism. For our use, since we already require a confidential client and must possess a secret, we can simplify the specification. So again, we limit the requirements and require the clients to use what is suitable for our case. Instead of Depop itself can be quite complex. There are many variations on the topic. But for our use, it's extremely efficient. We are almost ready to go into production with it. We are testing it now. Love to do it before, but Dominic, hurry up. We are based on Duenda Identity Server. So it's coming. And that means that this attacker that could steal the token, they can steal as many tokens as they want. They can't use it. It's no value as long as they aren't able to steal this secret as well. That's a good thing. In addition, we have a requirement that is also a future requirement that you need to call PAR, Pushed Authorization Requests. As you saw, if you go back one step to the figure, in the first step, you have the user logon. We will send quite a lot of information in the web browser. And there is always a risk that this information can be stolen and can be modified. So we don't really want to send information in the browser at all, really. You need to send some information, but with the pushed authorization requests, you send most of the information in a backend request. So you do an extra backend request before you do the user logon. You send all the information server to server, and then when you do the user logon, they just point to a session ID that we already know. It's a really simple addition, and it removes a couple of attack vectors. So this is also a future requirement on our side doing that. We expect to be ready early next year to go into production with that. It's on the way. Finally, don't do security yourself, guys, girls. Don't do it. Always use a library when you do security, and especially when we do protocols. We have a requirement that as long as there is a library available for your ecosystem, if you're on .NET, you're lucky. There are very good libraries there. On Java, there are quite a few good libraries. For most development environments, there are good libraries available. If there is a certified library, you should use that. But do not implement security protocols yourself if you can avoid it. It's lots of work. You're going to have security holes, so there's lots of work to fix them. You need to maintain this. So use a library. That's on our side, as long as it's possible, that's an absolute requirement. So this leaves us in a really good spot, actually. We know that a software that follows our requirements, it be an API, it be a client, they are quite secure. We know it's robust. We know that it handles the protocols well. We know we can trust it. But of course, how do we know if they actually have done this? And what else? What do we need to build this ecosystem? Because we have lots of technical requirements. And time is going fast, so I'll just spend a few minutes on the process side of things. That's the final thing we do. First of all, we do code reviews of all the software that connects to HelseID. All clients, all APIs, they all must go through a code review on our side. We have a dedicated team that work with the protocols a lot, so we've become quite good at this. It's quite fun as well. We have seen so many different things. But we do code reviews of everything, and since we have the security profile, we can say these are the requirements, and when people don't follow them, we say no. We say, sorry, you have to do this properly. You're not allowed to access our service. And this establishes trust. People can trust our service. They can trust the client software out there. And this gives us a really good ecosystem. And all the vendors out there, they're really happy for this offering as well. It doesn't take much time. We spend like 30 minutes, maybe an hour, going through the details. We give them a feedback. And in most cases, people take security securely. Some of them don't. They come back later and have taken security securely. So, of course, we only look at the integration with HelseID, how they do security, that kind of stuff. We don't look at the entire software. That would take a long time. But this gives lots of value. On top of that, we have established a self-service solution where you set up everything to use HelseID. We have both test and production environments. And you are able, in the test, you can do everything. Set up whatever you want, try it out. It's open basically for everyone, on the internet, in the health network, everywhere. But in production, you need to have a delegated access. It means that when you log on as yourself, we can look up in what is called Altinn. It's a common registry in Norway of organizations and delegations. And we can ask, is this person allowed to represent this organization? Yes. If they are allowed to do that, normally it's only the business owner that is allowed, but they can delegate it to some technical people. And then we have a very good proof that this client software actually can represent this organization. So we have that connection. And so we know that this is a health organization where they are in healthcare. We know that they follow the rules. We have registries of that, those kinds. And so we do a lot of beforehand vetting of the setups. And also this allows for scalability. We can allow anyone in without much work on our side. So it's a really important step for our service. And finally, we have the core service of HelseID itself. We have spent years with our team building the service, honing it, tightening it. We still do. There are daily pull requests. We spend a lot of time on the security of the service, on the availability, performance, protocols, protocol support, all that. We follow what's going on internationally, that we know we are in the front of the requirements. We do penetration testing, of course, with people who actually understand the protocols. We have a dedicated operations team that understand not only the protocols, but the entire ecosystem. So we spend a lot of time on the service itself. We know that it's robust, we know it's secure, we know it behaves well. And if something should happen, we have a good team that can fix things. And as I said, we don't invent anything ourselves. We build on Duender Identity Server. Really happy about that. It has served us well for years, and we're going to continue doing that. So thank you guys for that. And that's basically it. So to summarize, building a secure API is easy. Building a secure ecosystem where you can share this sensitive information, that's the challenge. To do that, we have our security profile that have these very tight requirements. We don't invent anything ourselves. We build on internet standards. And we have built an ecosystem for sharing information. And that's it. Now, I'll leave this slide on because it's a bit brighter. I think we have like a few minutes. Are there any questions? There is one up here. I'll try to... Yes?
So you said something about Windows XP machines
yes.
in your environment. So what are the current practices?
The question is about Windows XP machines in the environment. And I know that there are a few very old computer systems out there that are still in use. X-ray machines that only work with this operating system, for instance. I know that those machines, they are locked down behind firewalls, closed down. They're not allowed to access anything external themselves, and they control the traffic. They are, as far as I know, we don't have any clients to HelseID that are on those old operating systems. But we have lots of old programming languages. Delphi back from 2011. We have C, old versions of that. We have .NET back in the full framework versions. We have lots of older software that integrates with HelseID, but the same requirements apply. Anything else? Take this one first.
On GitHub.
On GitHub, yeah.
There's samples.
There are samples.
HelseID. Is this samples which we can trust and use? Or is it being maintained somewhere else?
Yes. That's a good question. We have, on GitHub, we have sample code for how to integrate with HelseID. That sample code is written by our team, it's maintained by us, and there are two versions of that. We have some sample code that is very basic, shows how to use the protocol in the most simple ways, and we have more complex sample that shows how you use many of our features together. And yes, you can trust them, you can use them, but of course it's sample code. So make sure that whatever is done there is done properly. For instance, we keep secrets in source code. Don't do that in production. But the code itself, it's you can trust it and you can use it. Yes. There was one question here as well.
Yeah, so before that, when we have this implicit type, we usually do this refresh token generation silently, right?
I'm sorry, it's a bit difficult to hear you.
So in implicit type,
Implicit,
we
yeah.
usually have this silent refresh token concept. You can generate the token, so how it works with authorized code.
You're asking about refresh tokens? Yeah.
Refresh code,
Yeah. Yeah. We have the concept of a refresh token is a way to keeping this user session for extended for a long time. In implicit, you have that concept, and you have the same concept with authorization code. The refresh token can be used against HelseID to get a new access token, because this access token that gives access to an API has a very short lifetime, maybe just, maybe just 1 minute. 10 minutes at max, because we are afraid of tokens being stolen. With the authorization code, you still can use refresh tokens, but require that you possess the secret, the same way as you do for other token delivery. It's the same endpoint, the token endpoint, but you must pass this signed object, which is called a client assertion, when you get the refresh token as well. So the same security measures apply. And when we introduce Depop will be required there as well. Anything else? We're almost out of time, I see. No difficult questions. No, there's one more.
Can you talk about the challenges of integrating HelseID with mobile technologies? You skipped that part.
Sorry, the challenges of integrating.
Like HelseID against the mobile.
Sorry, it's a bit noise from behind here.
Using the mobile.
Oh, mobile, yes. Yeah, I skipped the part of mobile applications.
Can you talk about the challenges that you...
Yes, I can, yeah, like I have 1 minute or so left. When doing mobile applications, we have this requirement of a secret. And a secret must be deployed somehow together with the installation of your software, because we require that the secret points to one installation of your software. In the mobile world, you have installations of each and every phone, iPad, whatever, and transferring a secret there in a secure manner, that's the challenge. It could be done in a manual way somehow, but it's going to be very clumsy. And that's basically the reason we aren't quite sure. There are mechanisms, what is called a DCR, that is a standard of how to set up new clients using an API that we could provide that may solve this. But the reason we don't really have a good solution for mobile clients is that it's quite difficult today to handle secrets. That's basically it. There are good mechanisms on a mobile phone, for instance, to protect secrets as soon as you get the secret inside the device itself. Looks like we're almost on time, so if there are more questions, please come talk to me. I have a colleague here as well. So thank you.